Hello everyone, today I want to talk about motion in polar coordinates. So really quickly, I want to do a quick comparison of Cartesian and polar coordinates. It will seriously help you if you've used polar coordinates in a math class before this, but in case you haven't, I want to let you know it isn't impossible and you can do this, okay? So in Cartesian coordinates, we're kind of used to like this idea of this 2D, I showed you the 3D one, but what we're used to really, like in math class, is this like 2D plane, and it looks like this, okay? There's a right angle here, and, everywhere, basically. Okay? Whereas in polar coordinates, we will still sometimes draw this in, and, I like to, personally. I guess you don't have to. But it's going to look a lot more like the unit circle in trigonometry. And I will show you why. There's going to be a circle that runs around here. Wow, that was actually pretty good for me. Don't know what happened there. So there's going to be a circle that runs around here. Already, as I hinted at in the last video, you can see why this is going to be necessary. If you haven't watched the last video, by the way, I really recommend you go and do that because I think it's a good example of why polar coordinates are very, very necessary and useful. Okay, so really quickly, just for a point, in the Cartesian coordinate plane, we know that's x comma y. It's called the ordered pair, right? We're used to that. In the polar coordinates, it's not too crazily different. It's r comma theta. This might make a little bit more sense if you watched the last video, but I will show you right here. So if we have some length r here, our point's right here, we can represent it with the length r and the angle it makes to the x-axis, which we call theta. Okay? And here, I would assume you know this, but 1 over in the x, 1 over in the y, that's 1, 1. Or in the format, x comma y. Okay, so I want to talk about something else. Continuing to compare and contrast the two, because I think that's a good way to get started in polar coordinates. It's always on focusing on what's different. So let's talk about unit vectors. Okay, unit vectors. So you're pretty used to this point, at least I hope you're used to, the x hat and the y hat unit vectors. And I think, as you can imagine, it's not going to be as simple here, because we might have a point that changes over time, right? Just like our position vectors on the clock from last video. And this point will just go around and around and around and around the circle, just like a second hand goes around and around a clock. This is why this is going to be useful. So our unit vectors are now functions of chine. And just like how this was x hat, x, y, we're going to have the r and theta hat unit vectors. Okay? Where if we have, let's draw this up super fast. If we have polar coordinates that look like this, r right there, angle of theta right there, our r hat unit vector will always point in the same direction as the radius of the circle is pointing at that time. And our theta hat will point as a straight line directly in the way that theta would move, which, as it comes out, is still going to be perpendicular, just like this is perpendicular here. And this is the theta hat unit vector. So here, to summarize, we have r hat in the direction of r, and theta hat in the direction in which theta moves, which is perpendicular to the direction of r, the radius. Over here, we have x hat, we have y hat, and if we want to go 3D, we could say z hat. But I'm trying to keep this 2D for now. Okay. The other thing I want to talk about really fast about unit vectors is that they're not the same in polar coordinates. They don't stay the same anyway. Because what we'll find is that as our radius moves around to represent a different point, like what if it's right here, right? What if it's right there? Well, then r hat will point in this direction. But I thought we said r hat points here, right? So r hat changes in time, and theta hat does too, for the same reason. So therefore, they're not constant. And that makes math with them a little bit more tricky, which is why I don't really go into the derivations of any of the equations. I could, but honestly, I think they probably will just confuse a young student who's trying to learn this more than they will help the student. And I shouldn't say young, like I'm a high schooler, but, whatever. Really quickly, I just want to talk about how you would represent a point and like its mathematical values here. So if we have the y, say like a y here, like this is our point in Cartesian coordinates. This is, the distance to the x-axis. There's our position vector, right? Pretty standard stuff at this point. We have a little right angle there. We realize we can use the Pythagorean theorem. And we can say that the magnitude of that vector r is just going to be equal to the square root of the x component squared plus the y component squared. Well, that's x, that's y. That's pretty standard. That's Pythagorean theorem. And then if we want to use that angle theta to the x-axis, what we can kind of say is that, well, x is equal to r cosine theta, y is equal to r sine theta, and that's really about that. I mean, we could also represent it in vector notation if we wanted to. We can do a lot of stuff with Cartesian coordinates. They're very important. Okay, you can also represent r as that, like I showed in previous videos. If you're not comfortable with that, go back to a previous video. There's no shame in trying to learn something twice. Polar coordinates are very different, but in this case, they are kind of similar. So here, I'm going to use this same formula. Pythagorean theorem. Okay, same as over here. We can use that same formula. If we want to calculate our angle, we can do basically the same thing. Say it's going to be the inverse tangent of the opposite over the adjacent, so y over x. Okay. And if you're not familiar with SOHCAHTOA, that will be confusing, but know your trig functions if you're in physics. I do have to assume that you know some math. I'm sorry, I try to make the math in this as easy as possible, but at the end of the day, I do actually have to know that you assume that you know something, or else we'd be here for absolute hours. And that's just not very pleasant. If you want me to teach math, leave that in the comments below, because maybe I will one day. Who knows? Anyway, so we can, using this vector notation, this is where things will get a little bit different, because our unit vectors have changed. We can always say that our vector r is going to have a length of r in the r hat direction. R always has to point in the direction of r. That makes sense. Okay? And we can separately describe theta. It's not very useful to put these two together, to be honest, because of the moving vectors. It makes things very complicated. Whereas if we just describe theta independently of that, theta always has a magnitude of theta, and it will move in the theta hat. I mean, I guess you could kind of say it's in the theta hat direction, but it's really more like theta hat's more decided on where theta's going to move. Oh, whoops, I didn't even realize you can't see part of that. Move in the theta hat direction. Okay, So I guess I will label this section the math. Not the math, the math. Anyway, now this can be kind of confusing, and really how you learn motion in polar coordinates, at least as my textbook teaches it, and how I think it should be taught as well. I agree with the textbook. You just kind of have to do problems with it. It's weird, but you already know most of the basics to it. I taught a lot of the basics to most of the problems, our uniform circular motion. Taught that in the last video. Okay? So I actually want to do a problem that's considered a little bit more advanced and walk you through it. Because I think if you see a really, really advanced problem, and obviously attempt all the problems on your own first, if you want to. If you think there's just no way you're going to get it, just watch it. But what I do really encourage you to try that on your own first. But I'm going to walk you through a little bit more of an advanced problem, because if you see how to do an advanced problem, you can probably apply it better to an easy problem. If you want me to do easier problems and you think that's better, just leave a comment and say so. And I will do easier problems as examples. Okay? All right. So here I want to talk about a problem where we are going to have completely uniform motion, like our numbers aren't going to change or anything like that. There's no acceleration. There's no angular acceleration. And there is no radial acceleration, but we are just going to have a constant radial velocity, which is already different from our clock, right? Radial moving outward. Yikes, that's kind of scary. But here's why polar coordinates are so much more powerful. Okay? So, very quickly, what I want to show here is an example. So, all right. We are going to take this wheel, okay, and you have to kind of think back for this example. I guess this might not be the greatest example to connect with really any audience today, but so it's like a wheel on a horse-drawn carriage. I promise you it's not that ancient. But it has all these spokes, right? Now I'm drawing them in awfully, but okay, it has like 50 million spokes on it. Okay. But on one of these spokes, there's this little dot I'm drawing in that's a bead, okay? And the bead is going to move that way. You can't really see that vector. Let me try to make that a little bit darker. Okay? It's going to move in this way, which I will call the r hat at this time. Now, you can imagine the wheel turns, right? So, expect there to be some kind of change in the r hat direction, and by proxy, the theta hat direction. We're going to call this the angle theta. Okay, because that's, I guess, where we're just going to assume it's at t equals theta naught. Okay? That's where it is, and that's kind of like along the x-axis, so to speak. Though we don't really have an x-axis, we can still kind of use elements of Cartesian coordinates in this. So right here, I want to say that my tangential velocity, aka this velocity vector here, and in this case, this velocity vector is going to be equal to r times omega, where omega is the angular velocity, which is equal to the change in theta with respect to time, or the derivative of theta with respect to time, if you want to know the instant. Okay? And here, r is going to be the distance of the speed from the origin, which, we can really call it really right about there, because that's the starting point. You really don't want your origin to be the exact center, because then we're going to have some initial position or not, which is just not worth your time. When you can define your coordinate system to be anywhere you want it to be, why would you define it somewhere where it makes your problem more complicated? And you might think that polar coordinates make problems more complicated, but as I'm going to show to you, they really don't, if you use them right. Don't use polar coordinates for every problem. That's just a headache. Okay, so we're going to say that r here is going to move with time. Okay? In other words, the speed will expand out over time, and it will have some limitation, but we're not going to focus on that right now because obviously it's going to hit the edge of the wheel. And we are just going to say that r equals some speed u times t. U is often what we use when we run out of v's in physics to represent speed. But, okay. So, really quickly, this will come in handy later. The derivative of r with respect to time is just equal to u, right? Cancel out that t. Power rule. This will also come in handy. The second derivative of r with respect to time, which would be like an acceleration, whereas this is speed, this would be acceleration. 0. Okay? Because the derivative of any constant, u is a constant, 0. All right. So after some, initial definitions, I want to talk very briefly about the equations of motion for uniform, or not uniform, circular, but in this case, kind of circular motion, polar coordinates. So our wonderful kinematic equations in polar coordinates. So velocity is going to be equal to, the velocity, right? The dr over dt, the instantaneous change in velocity, or change in position, rather, with respect to time, r dot, and it's going to point in the r hat direction. Plus r, so our position, times omega in the theta hat direction. And if you look, all we're doing in polar coordinates is just taking this equation, which I introduced in the last video, and we're just putting it within our polar coordinate reference frame. So I hope that makes sense. An acceleration in polar coordinates, and this wheel could accelerate, to be fair, because we don't know. Maybe the horse that's pulling the buggy, which this wheel is on, accelerates at some point. So angular velocity doesn't necessarily have to be constant in every case. In the case of a clock, it is. In this case, it might not be. And angular velocity, just as a reminder, is the change in angular frequency with respect to time. The derivative of angular frequency with respect to time. Or not angular frequency, angular velocity with respect to time. And this is going to be angular acceleration, which we use alpha. It kind of looks like a fish. Okay. So, the acceleration vector in polar coordinates is going to be a little bit more complicated. So, we're going to take the second derivative with respect to time of our position r, which is really just the acceleration in that, minus r times omega squared. And that's going to be in the r hat direction, plus the quantity r times alpha, our angular acceleration, so the rate at which the rate of change in theta changes, plus 2 times r, change in r with respect to time, derivative of r with respect to time, r dot, and then once again times our angular velocity. And that's going to be in the theta hat direction. All right. Now that I've introduced those equations of motion, we can go ahead and get to work. So if you're wondering why these are so complicated, it's because in polar coordinates, the integral of acceleration as a function of time with respect to time is not equal. Do not ever say that it's equal. Seriously, do not ever say it's equal to velocity as a function of time. That holds up in Cartesian coordinates, but it does not hold up in polar coordinates. As you can see, you can't just take the derivative to hop here or the integral to hop there. It does not work that way. Don't use it, okay? And it's mostly due to the change in unit vectors and things like that. When direction changes, things get complicated. Okay, but we're going to try to write a simple equation using this, okay? So if we want to write the velocity as a function of time, which will be our first step, I think we're going to write both velocity and acceleration. So if you want to, pause the video here. Go ahead and try to find that on your own. I wouldn't really expect you to do it from the very start of me giving you the problem because you don't have these equations yet. Okay? You need these equations first, right? But now, go ahead and see if you can do it. Take a shot at it. It's really not as hard as you're going to think it is. So, okay, I've given you ample time. Okay, I'm going to start. Okay, so we have the derivative of r, the position with respect to time here. That's just u. We already said that. Okay? So our velocity as a function of time, it's always just going to be u in the r hat direction plus r, which we can really say is r speed u times t. ut, and then our angular velocity. Okay. And we're going to call that the theta hat direction. All right, moving us down a little bit more here. Acceleration is a function of time. We're basically just going to do the same thing, plugging in. So the second derivative of r, I'm going to move this up a little bit more, which we already set up right here, 0. So there's no acceleration in the r hat direction. In fact, I'm not even going to write that there. Okay? Don't even worry about that. So now, but there is going to be some stuff going on in the theta hat direction. We already said angular acceleration is going to be non-zero. So, looking at this, we have r times alpha, our angular acceleration, the rate of change of the rate of change of our angle theta in time. So we have that plus, oh, and I forgot, I shouldn't write r. I'm going to sub in for r here, and we're going to sub in ut, just like in the last one. That's my bad. Okay. And I'm going to put a parenthesis there because we're going to have more to write in this. So plus 2, first derivative of r, it's just u with respect to time. I always forget to say with respect to time. Sometimes my brain thinks and my mouth just does not translate everything. And then omega. Really quickly here, I do want to note that we might be able to simplify this further. Just for simplicity's sake, I'm going to say that our angular acceleration, alpha, is equal to some constant number. In other words, it doesn't change. Well, we can go right here, and we can do the same thing that you could do to get a function for theta with this. Okay, in other words, we're going to multiply either side by dt, and we get that this really, really small angular velocity at some very, very, very infinitesimally small time, t dt, and then dt is going to be multiplied by the acceleration, angular acceleration. My bad. Take the integral by either side, and we get that omega equals alpha times time. Or in other words, our angular velocity is equal to our angular acceleration times time. We're going to assume that angular acceleration, that our initial angular velocity is 0. Zero radians per second. All right. So we can go ahead and sub this in for omega. And just as one final thing, so our velocity as a function of time equals u in the r hat direction plus ut. Actually, I'm going to write this in a little bit of different order. U times alpha, but then we have a t from the ut. We also have a t here, so we're just going to write t squared since there's two of them, multiplied together. Okay, and this is going to be in the theta hat direction. All right. Whoops, broke my lead. Oh my gosh, I'm doing it again. Sorry, I do apologize for that, but I have to kind of press down on the paper rather thickly, just so everything comes up on the video, and I know it will come up on the video. Okay, so now we can go ahead and say this is still going to be 0 in the r hat, right? The bead is not accelerating any further, like on the spoke of the wheel. Like, remember, it's not going to accelerate this way in the r hat direction. Okay. So now if we want to write the acceleration as a function of time, well, we have alpha popping up here. That's fine. Ut alpha plus 2 times u instead of omega. Funky looking w. We're just going to replace this with alpha times time. Angular acceleration times time. And that is going to be in the theta hat direction. Whoops, I did forget to write that up there, didn't I? That's my bad. Okay. And yes, if you really want to, you could write this in much simpler terms because you can do factoring. But it's honestly kind of useless in this case because you just factor out u times alpha times t in both equations and just be left with that quantity times 1 plus 2 all in the theta hat direction. I think that's basically useless. If you're factoring out everything, it doesn't simplify the problem that much. All right. So these are going to be our answers to the velocity and acceleration as a function of time. Really quickly, I just want to go over conceptually why this is the way it is. Moving at some constant speed u, it adds up that our velocity in the r hat direction is always going to have a magnitude of u, that speed. And it's not going to change because it's constant speed. Now, in the theta hat direction, or in other words, how our angle theta is going to change, it should make sense that we are going to have it change in time according to our angular acceleration. Okay, and here, remember, acceleration, in this case, the magnitude can increase even though there's an angular acceleration in the theta hat direction. I know that's not overly intuitive, but it can. You just kind of have to trust me on that. But it's not intuitive, as you would think. Because acceleration, you would think it would be constant, but because of all the math I've done here, you can obviously see that it's not fully constant. Okay? And then just as one final note, there's no acceleration, constant speed in the r hat direction, so it should make sense that our vector component of acceleration there is just going to be a big fat 0. 0 r hat right there. Okay, well, that is going to do it with this video. If you like this video, give it a thumbs up, subscribe. I'm going to post daily for a while here while I'm still on summer break. But yeah, thank you for watching this video. I hope you have a good day, night, afternoon, wherever you are, whatever time you're watching. See ya.